Welcome everyone to Snowden Optiro Fresh Thinking Series podcast. My name is Senzeni Matondi. I'm a principal consultant based at our UK office in Bristol. I'm joined here by my colleague, Laurie.
Yeah, thank you. Laurie Hassall, senior consultant in Geology in our UK office. Thank you.
Thank you. So today this podcast is a follow-up on our industrial minerals podcast that we did with Laurie together. And today's is going to be about silica sands more than just
Yeah, more specifically, we're going to get into more detail into silica sands. Yeah.
All right, thank you. So, Laurie, what exactly are silica sands and why are they important?
Yes, yeah, great question. Well, silica sands are, they're naturally occurring materials. So we're talking about an industrial mineral here, composed primarily of quartz, so silica oxide, and they're crucial in a wide range of industries. Glass making has been around for millennia, since the ancient Egyptians. Yeah. So, and obviously we still produce glass to this day, and obviously it's evolved. The science of making glass has evolved over many years, and now in terms of ultra-modern glass, we're talking about semiconductors, photovoltaics, also advanced ceramics as well. So many uses for silica. So they're a unique combination of chemical purity, physical properties, make them indispensable across glass manufacturing.
They're used across the board.
Across the board, yeah, that's
absolutely.
Right. Yeah.
So what sets silica apart from other industrial minerals?
Okay, so unlike many bulk materials, silica sand is defined not just by its silica content, but also its absence or near absence of impurities. For most industrial uses, especially PV glass, photovoltaic glass, even trace levels of iron oxide, for example, or titanium dioxide can cause defects or discoloration of glass. Making it sort of green glass, for example. Whereas for ultra low impurity threshold, elevate silica sands into a specialty market where geometallurgical precision becomes essential. So it's all about reducing the impurity level within the glass, and by doing so, you naturally elevate the silica dioxide percentage anyway.
Yeah. So as we delve deeper into geometallurgy, what are the geometallurgical factors that influence silica sand's suitability for various products?
Yeah. So in terms of silica purity, so SiO2, so we're typically looking at over 99.5% SiO2 for most glass applications.
Yeah.
In terms of iron oxide at Fe₂O₃ levels, it depends on the glass specification, but for the highest purity PV glass, you've got to be less than 100 ppm, 150 ppm iron, and then there's other thresholds above that. But for the highest quality.
So amazing, the relationship between iron and silica, because they always occur together. For an iron product, you want it to have as less silica, and vice versa.
Exactly.
For silica products, you want it to have as minimum iron oxide as you can.
It's that relationship. Yeah, you're right, exactly right, Senzeni. And there's also iron isn't just iron as well. So with silica sand deposits, it can be coatings on quartz grains themselves, so sort of staining of quartz.
Yeah.
But it also can be sort of free particles of hematite, for example, or limonite, which tend to be easier to process and remove, whereas sort of stained quartz is much harder, and you have to involve some acid leaching processes to remove it. But some other parameters that are key for silica sands. It's not just chemistry. We're also talking about grain size distribution. So typically for glass, you've got to be in the size range of sort of 150 to 600 microns. That sort of size range is typical for glass. Grain shape and surface texture also very important. And all of this is important because of the response to processing. So, how easy is it to remove the deleterious materials like iron, but also things like clay coating can be also a nuisance. Aluminium content, therefore. So getting the right technique, the right processing technique, and the appropriate technique for your silica sand deposit is key.
Is key as well. Yeah. Right. Okay, so can you walk us through a typical processing pathway for silica sand?
Sure. Yeah. So in terms of typical pathway, first stage is always screening. So obviously getting the correct size fraction, so that 150 to 600 micron fraction. Attritioning is also very important, so that's a key stage, is removal of clays and other free particles that are going to affect the process further down the line. The next stage is then sort of followed by gravity separation. So typical gravity separation techniques like spirals, tables, but also heavy liquid separation, dense media, to remove sort of denser contaminants like iron. So any free iron particles like hematite, you can remove those with gravity. And then finally, sort of a cleanup stage often involves magnetic separation. So again, final sort of removal of iron and to increase the silica content of the final product. And that's the sort of final stage in terms of physical processing, mineral processing. Dependent on the product, if you're going for sort of photovoltaic class, it might also be appropriate, or might also be required. It's sort of an acid leaching step. So acid leaching the quartz grains, removing some of that iron staining and improving the quality and the purity again. Yeah.
So I'm more curious on how the whole mineral resource estimation is conducted for silica. How does that work out? What does the resource estimation look like for silica sands?
Yeah. So silica sands can occur in lots of different sort of environments. So beach sands, might be alluvial sands, might be sandstone, primary sandstone, for example. But understanding lithological domains is obviously key, but also understanding alteration domains. So where there may be some deep weathering zones, lateritic zones within the silica sand deposit is key. And that will help constrain, some of the iron within the deposit for you to estimate iron, estimate aluminium, and estimate silica. So obviously we're not just estimating SiO2, we're estimating all the chemical impurities. It's also key to estimate the distribution, size range distribution within the deposit as well. So as we mentioned, the final glass product is usually within that 150 to 600 micron size range. So obtaining information on the percentage reporting to that size fraction is also extremely important. So all your samples need to go through particle size distribution tests, and then you can estimate PSD into your block model as you would do chemical assays. And you can take it to the next level, with more geometallurgical data. So, for example, final product silica and iron values can also be inputted into the block model as well. So you can estimate the final product distribution within the block model. So you're not just reporting the deposit as it is, but also reporting the deposit with the processing upgrade as well, which is key for industrial minerals.
Yeah, that's super. So how is the silica sand marketing? The market, how is it evolving?
Yeah. So I guess it's transitioning from sort of more of a bulk material view to a critical mineral narrative. So So obviously we hear a lot about lithium and other critical metals. Silica is a critical metal. As we know, it's used in glass and in everyday technology. So from obviously phones and everything we use uses silica. So it often gets ignored, in that conversation, but it's nevertheless
great that we're
important.
talking about it, eh?
Yeah, that's it. Yeah, that's right. Yeah.
So what do you envisage the next world of silica sands? What's next?
Yeah. Okay. Yeah. I guess with silica sands, it's, as I say, it's all about geometallurgy and understanding impurities, that kind of thing. So there's the purer silica sand deposits around the world. There's less of them. We're perhaps going to have to mine dirtier deposits, so to speak. So understanding geometallurgical properties of deposits will be critical. So more advanced sort of domaining and maybe machine learning and resource modeling may become important. From a processing perspective, sustainability in terms of processing will become more and more important. So obviously reducing the amount of water that we use when processing silica sands. Obviously, there's a lot of screening involved and nutrition. It's gravity separation involves a lot of water. So.
So basically, we can say that there's two big trends, right, in the next world for silica sands. It's your digital metallurgy there, and geometallurgy and sustainability, which is a very important topic nowadays.
For sure.
We need to have the sustainable environment. So to wrap up this whole discussion on mineral sands, what concluding statement would you like to share with our viewers?
I guess. I guess more consideration about silica sands. So the next time you walk on a beach, for example, remember that those grains beneath your feet might just be the next frontier in solar panels, smart screens, sustainable buildings, etc. So silica sand very important for the modern world and the future world. Yeah, exactly. Yes.
Thank you so much, Laurie. That was very enlightening. And thank you for watching, and hope to see you in our next Fresh Thinking episode.